So welcome. So this is oscillatory motion. It's first part of our first 4 chapters, which is on oscillations, and then we look at waves, and then we look at sound, which is the application of waves, and then we look at basically interference. And this is really bedrock. We're going to use the math that we use for this section throughout this whole semester, because if you think about it, the electricity that comes out of the wall socket is AC, which is an oscillation. If you think about it, light is like a wave. So we're basically going to use oscillations and waves throughout. I want to show you something before we begin. So this may not be so elegant, but let's see how it works. I want to do that. Please, I want to do that and that. And then let's do this. So let's go back to the beginning. So what we got here is we've got a red dot that was moving with uniform circular motion. And we have a pendulum. The pendulum oscillates with a certain type of oscillation called simple harmonic motion. It's very common in the natural world. Well, just various examples. When things vibrate elastically, they vibrate with simple harmonic motion. Pendulums, masses on springs, but phonons going through solids. Even the electricity coming out of the wall has the same curvature to the graph, which is simple harmonic motion. And simple harmonic motion, it turns out, is like one component of uniform circular motion. So if you think back about when you did, centripetal acceleration and all that kind of stuff, we can use the math that we learned from uniform circular motion to describe oscillations and waves from now on. And here's the justification. So what's happening is this student is going to release the pendulum right when the red dot is aligned with it. And I want you to look at the vertical positioning of the pendulum and the red dot. So don't worry about how high it is. Worry about how far it is across the screen. So maybe I'm asking you to look at the horizontal positioning of the two of them. So let's just look at this. There's probably sound, but, we'll see. So it's going to wait. And I'm going to stop it at various places. And they're saying, oh, look what happens. I hope this is not the joke one where she doesn't actually let it go. And you can see, stop, stop, stop. I should need to be over there. Stop. Can you see? They're in line with each other. Stop. They're in line with each other. Stop. They're in line with each other. Stop. They're in line with each other. And so on. So what that means is that I can mathematically express not just the position, not just the velocity, not just the acceleration. I can mathematically express position, displacement, acceleration, velocity for the simple harmonic motion using uniform circular motion. So it makes our life actually much easier. So that's where we're going to over these next little while. So we're going to talk about, first of all, today is all about oscillations. So we're going to talk about what is simple harmonic motion, then acceleration at a given displacement. Imagine that you're like this kid who has learned some mechanics, and you just want to apply it and see what you can figure out for something new. And that's kind of where this chapter goes. It's like, can we figure that out? Can we figure this out? Can we figure that out? And it turns out you can figure out a tremendous amount based on your general physics 1. Of what's going on with these oscillations and waves. So that's the game we're playing. Well, what would the displacement at a certain time be? What would the velocity at a certain time be? What would the acceleration at a certain time be? And so on. So that's what we're doing. And then towards the end, we have these last 3 bits which are to do with, actually these last 2 bits, which are to do with real systems. And real oscillating systems have a thing called damping in them. And so we'd like to talk a little bit about damping. It turns out the math we need to discuss this is basically differential equations. And differential equations are not part of the prerequisites for this course. And they never are. It's not like everybody else is doing it, but you're not. They never are. So what happens is the textbooks tend to pull the answer out of a hat, which I find a little bit discouraging, but that's the way it goes. So we'll talk more conceptually about damping. Okay, but if you're up for it, you can, and you've done differential equations, you can look into it some more if you want, but you won't be tested on the mathematics of it. Cool. So let's begin. So what is simple harmonic motion? An object moves with simple harmonic motion whenever its acceleration is proportional to its displacement from some equilibrium position and is oppositely directed. Oh my word, if ever there was a need for an equation to cut out the gobbledygook, that's it. That's what I just said. When the restoring force is proportional to the distance from the equilibrium and oppositely directed. And that is good old Hooke's law. Hooke was a contemporary of Newton. He was 7 years older than Newton. Hooke was responsible to a large part for the establishment of the Royal Society, which is the first peer-reviewed science society. It's still in existence today. Newton looked up to Hooke tremendously. Newton felt he was burned by the Royal Society. He never forgave Hooke. Newton succeeded Hooke in terms of being in charge of the Royal Society and basically erased Hooke. Hooke did an awful lot of stuff. All he's left with is this spring thing. It's so sad, really. He was a very important person, and yet people only know him for this one thing. The classic thing is the mass on a spring that obeys Hooke's law. You probably did it in Physics 1. We don't really care about masses on springs that much. We care about phonons going through crystals or AC or light. But it turns out all those things follow this same pattern. So we say a block on a spring combination is a simple harmonic motion system. It looks, if I imagine underneath here drawing a graph, it looks like a sine curve or a cosine curve, depending upon where you start it. Not all oscillations look like that. You could have an oscillation which was sawtooth. You could have different types of oscillations, but the ones we really care about, the ones that we care about are the simple harmonic motion, and they follow the sine curve or a cosine curve, depending upon how you start the thing off. So we say a block and spring combination is a simple harmonic system. Consider a block that is attached to the end of a spring. So here's my spring. It's level on a desk. Frictionless desk, of course. And then I move it to the side and I simply let it go. I don't push it, I don't shove it, I simply let it go. And so what happens is it starts off from here and basically it moves, and it gets faster until it gets to the equilibrium position. Then it slows down because the spring now, it's like a car spring. It's squashing it is hard, stretching it is hard. So it slows down, it stops, it speeds up again, it slows down, it stops, it speeds up again, and so on. So let's be clear about this. I'm plotting time here and position here. So what I just plotted is a graph, and we've got to be careful about what we plot, what our diagrams mean, because we can get things confused in this next couple of sections. So I plotted a graph of position versus time. It had in this case, it had a cosine relationship with position and time because I started off and let it go. The block can slide horizontally across a smooth table. So we have two fundamental governing principles. We have Hooke's law, and we have, well, Newton's law. They both must apply. So I say, oh, well, that force there must equal that force there. So that means that minus kx must equal ma. I'm interested in acceleration. My acceleration is equal to minus kx over m. And for various reasons, people like to light things in different ways. Minus k over m times x. It's all the same stuff. So we just did our first bit of insight by derivation. We took two things that we're familiar with. If we weren't familiar with Hooke's law, we get familiar with it. We took two things that we're familiar with. We say they must be equal to each other. We substitute, rearrange, and we get an insight. Literally what this means is if I know the displacement, if I know the x position I can figure out the acceleration. It just falls out. Now, I can't figure out the velocity from this, but I can figure out the acceleration. So it's a little bit of a game. It's like, oh, I can do that. That's interesting. In simple harmonic motion system, is acceleration constant for different displacements? So I want you to think about what we've just said and answer that first question. So you're anonymous. I have no interest in tracking you personally. I think that it's distracting. I want you'll know whether you have the right answer or not. But I want you to have a go. So 13 people have had a go. In simple harmonic motion, is acceleration constant for different displacements? That's the question. Got a question or comment? I'd never used one actually. Do we have to send? No. You turn it on, you've got to click the button at the top, and then... I should have practiced with them, but I never have practiced with them. So now we've got 23 people. Maybe somebody stole my batteries. Okay, yeah, grab another one. Is there another one? Yeah. So I'm going to end it in a few seconds. We've got about 30 people, got 24. I'm happy with that. Any more before I close the door? Okay, I stop it. And then we can see this, and most people are saying B, a couple of people are saying A, a couple of people are saying C. What is the answer? Well, if we think about it, what we said was, I've got to go down here again. That is so annoying. Excuse me 1 second, I've got to go and find my pen. There we go. There. So what we said was A was equal to minus K over M times X. I think that's what the equation said. And X, of course, changes my displacement. As X changes, my displacement changes. And A is not constant. A is certainly not constant. As X changes, A must change. So the answer is no. The two are not the same. So there's an example of we developed an equation, but we do think about what it means physically. Try and get out of the habit of seeing equations as magic formulas that you just plug numbers in, you get an answer. Think of them as shorthand for a concept. And you can interrogate them, and you can work out an awful lot by just messing with that equation. What kind of relationship links acceleration and displacement? I'll do this one. Well, let's have a look. A is equal to minus K over M times X. Well, that looks a bit like Y is equal to slope, X plus B. Isn't that? K's not changing, M's not changing. K depends upon the spring stiffness. For a given spring, that's not going to change. M depends upon the mass's mass. For a given mass, that's not going to change. So these guys are not going to change. They're a constant. And so what I get is, that's linear. In simple harmonic system, is acceleration constant for different times? Now we need to think about this. That equation links displacement and acceleration. But visualize what's going on. Imagine a stopwatch. Imagine the time changing. So now answer me the question about time versus position. Time versus acceleration versus time. So it's not the equation, but it's what the equation implies. It involves visualization. You've got to, okay, I know what's going on. I can see things. What do you think? And on these bits, I don't actually mind you talking that much because you can talk to your friend and say, what did you get? Man, you're crazy. All that kind of stuff. but you can't stand up and threaten them. So let's stop it now. Okay, what do we get? And now it's a bit more split. Now, some people are saying A, which is yes, simple harmonic system, acceleration is constant for different times. And some people are saying no, it is not the same for different times. And some people are saying sometimes. These are the politicians down here. It's like, you know, like, good parents. But the answer is that the acceleration is not constant for different times. Because if you think about it, if that's true, if A is equal to minus k over m times x, and x is dependent upon time, which clearly is. We did a graph where we showed time going downwards, and we showed x here. In different times, we have different x's. With different x's, we have different accelerations. So again, it's going from that. I suspect the people who said A said, oh, t's not in my equation. And it's not. But x depends on t. So again, it's going from that. It's making the equations your servant. You're not there to feed the equation with numbers. The equation is there to give you insights. And so it's pulling these things apart. It's just a shorthand expression for things. Okay, well, that little bit of derivation was kind of gave us some insights. I would not have been able to answer those questions just by thinking about it. That derivation really helped me get some insights that I didn't have before. Let's do that some more. And that's really the lesson of physics 2, is that we spend a lot of time deriving things, learning more physics by combining simpler physics that we already know. That combination of things is really useful. So let's do a bit more of that. So here we have a physical situation. I have a light source or a camera, and I have some kind of can sitting on a turntable, and I have a pendulum swinging at the back. And what I find is that if I set these things off at the right time, then the can or the dot is always in line with the pendulum bob, like we just saw in that little video. And so if that's true, we should be able to do some mathematics, because the uniform circular motion bit is keeping track of the simple harmonic motion bit. So even though the pendulum, even though the mass on a spring is not going in a circle, it's a linear motion, I can model it. I can describe it by taking, in this case, the x component of circular motion, because they always line up. So I say uniform circular motion is directly related to simple harmonic motion, and we get used to UCM and SHM. You know, we kind of get to know what that means. And what we do is we say, okay, here's what's going on. Here's my red dot, and it has a certain tangential velocity. Let's call that VT. And it has a certain centripetal acceleration, let's call that AC, and it has a certain displacement from equilibrium, let's call that x, and it has a certain angle. So as time passes, this red dot moves around the circle, and as it does, x changes in time. My x component of my tangential velocity changes in time. My tangential velocity does not change, but it's pointing in different directions as it goes around the circle. So the x component changes in time, and my x component of my centripetal acceleration changes in time. So the x position, the displacement, is the displacement that a pendulum would have going backwards and forwards at any instant in time. The x component of my tangential velocity is the velocity of my pendulum, and the x component of my centripetal acceleration is the acceleration of my pendulum. Question or comment?
Yeah, is the tangential velocity perpendicular on the central acceleration?
Tangential velocity is always perpendicular to our centripetal acceleration, yeah.
So why don't you just connect them together?
Because I don't know. It's why. I mean, let's talk about that afterwards. Why would you connect them together?
Wouldn't it be easier to get the?
I mean, that could be like that, and that could be like that. Or maybe if it's going faster, that could be like that. They're not direct. They are linked mathematically, but not on a diagram. So it's not clear what you mean by connect them together, but just go with me for a while. Okay. So the issue is we got to represent our angle in terms of time. Now we're used to measuring angles in degrees. And the problem with that is degrees are completely made up. 360 degrees is completely made up. If a space alien comes down, they won't know 360 degrees. Historically, this comes out of, I think, basically Mesopotamia. It's somewhere, basically, western or eastern Syria, eastern Turkey, that area. They had a base 6 number system. And so they divided things up based on the number 6. And so it was a better number system than anybody else. So you ended up with a situation where they were better at astronomy because they could measure angles better than anybody else. Because they were good, they were remembered. So they've come down. So if you think about it, we have 24 hours in a day. That was bad. We have 24 hours in a day because of these people. We have 360 degrees in a circle because of these people. We have 12 months in a year because of these people. Historically, it's come down. Well, we sometimes change things. We don't go around with muskets because people had muskets. We change things. We change things when they're better. So to some extent, there's something good about these numbers. And better than base 10. It's kind of interesting. It's better than base 10 in some regards. And the reason why it's better than base 10 is if I have 12 months in a year and I'm your landlord, I can say, well, you can pay me one time every month, so that's 1 times 12, or you can pay me 2 times every other month, which is 6 times a year. You can pay me 3 times every 4 times a year every 3 months, or 3 times a year every 4 months, or you can pay me 2 times a year every 6 months, or 1 time a year every 12 months. So there's a whole bunch of choices. Whereas if we had a base 10 system, there's 1 times 10, there's 2 times 5, there's 5 times 2, there's 10 times 1. There's not as many choices. So it turns out that base 6 is actually quite useful. It's lousy for doing sums, but it's really good for dividing things up. Try and divide a cake into 10 equal slices. Good luck. It's a pain. Okay, but you can do it into 12 easily. So it's made up. It's highly likely that aliens didn't have our history, so they won't recognize degrees. But they will recognize the radian. And the radian is basically you take your radius and you run around the edge. And when you've run 1 radius around the edge, that's 1 radian. 2 radians around the edge, that's 2 radians. 3 radiuses around the edge, that's 3 radians. Turns out there's a little bit over 6 radians in a circle. It's not a whole number, so people don't like it. So approximate. Call it 6. Who cares? It's a big degree. It's a big slice. It's not, all right, we can divide it up into milliradians. We can live with it. But anybody over the universe will recognize that unit. It's a really good unit. So we tend in physics 2 to use radians a lot. And so we want to recognize how fast something is going. We can talk about revolutions per second, or we can talk about degrees per second, but we prefer to talk about radians per second. And we call that angular velocity, which is omega. Now we're going to call it angular frequency because it's going to could be good shorthand. If I want to know how big an angle I go through in a given time, I got to multiply this radians per second times seconds gives me radians. So, omega t. If I take the radians per second and I multiply it by the number of seconds, I get the number of radians, which is how big an angle I get. So that's a little bit of a switch on us. It's not theta, it's omega t, but we get used to it. Okay. So the angle changes with time, so it's best to express it as omega t instead of theta. Angular speed, omega, is often referred to as angular frequency in this section. An object displays uniform circular motion. It has an angular frequency of 6 radians per second. How long does it take it to revolve through 30 radians? So 6 radians per second. That is my omega. Is equal to 6 radians per second. And I'm interested in the time to go through 30 radians. Okay, that would be a theta is equal to 30 radians. So I'm going to say, using dimensions, I can say my omega is equal to my theta over my time. So my time is equal to my theta over my omega. My time is equal to 30 over my 6, which equals 5 seconds. So if you want to know how long it takes to revolve through something, get the angle and divide it by the speed. Now, I don't know how you feel about that. I feel uncomfortable about that. Every time I do this, I feel uncomfortable about that. But if I said to you, you drive at 60 miles an hour, you're going to go 120 miles, how long do you drive for? You could do it in your head. It's the same mathematical problem. It's just the language is very comfortable in one case, and the language is very uncomfortable in the other. So there's a lesson there about an awful lot of what we face is not mathematics. The math is easy. It's the language. It's what the equation means. So a part of your job, don't do what I did. I spent all my time trying to learn more and more math and get better and better, and I wasn't particularly good at math, so it was my real weak spot. I didn't spend any time on definitions. So when I came to the exam, I didn't really understand what the question was about because, man, what does that mean? I wasn't sure. So you got to sweat the details. And that's partly why reading the book matters. That's partly why watching videos matters. That's listening to the language. You're learning a language. And the more comfortable you are with the terms, the more comfortable you are with the terminology, the vocabulary, the cadence of it, how you speak. First of all, the more you'll fit into the physics or engineering club, which is important. And secondly, the easier it will get. So sometimes it's not, in most people's cases, it's not the fact they can't do the math that limits them in physics. It's the fact that they do correct math on the wrong problem. So this is part of getting the right problem. Not being cornered by something, breaking it down. Just by the by, there's the guy that does the Daily Show, whose name I cannot remember. Trevor Noah. Trevor Noah, very interesting guy. I heard an interview with him on the radio, and he was talking about how he was born and raised in Africa. I think his mum was black and his dad was white, and at the time that was illegal. So he had this issue about fitting in and the like. He tells a story about seeing his dad at a park and running towards his dad and wanting to play with him. And his dad, realizing that that's illegal, running away from him. And Trevor Noah, thinking that he was playing hide and seek, so kept running after him even more, shouting after him, and his dad sprinting away from him. Terrible situation. His mom was really keen that he was able to go from culture to culture. Just as a ton of cultures in Africa, it's a continent. And what he found was, there was this one time, he was very good at mimicking voices. and his mom was from she had English, which she spoke in South Africa. She had Afrikaans, but she also had her native language, and she was keen on him learning as many languages as possible. And he said he was in Johannesburg, I think it was, and he said there were 3 guys walking down the street, and they clearly, they were from one part and he was from another part, and they were going to mug him. And he recognized where they were from, and he spoke to them in that language using a good accent. And they apologized to him and said, "Oh, sorry, man, we didn't realize you were one of us," kind of thing. He didn't look like them at all, but he could speak their language, and so they were he was part of their group. And he said, "I think that the way you speak is really important for acceptance. If you can speak the same way that the listener hears, you become accepted. It doesn't matter what you look like. You speak and you get accepted." And I think it's the same with engineering in a little way. If you know the vocabulary, then you're in the club. And if you might be really bright, but if you don't present it, if you don't speak it in the right way, then you'll always be a bit of an outsider. And you want to be accepted in the next levels. You want to be, like in that class, you want to be an engineer. So it's important that you learn the language, etc., etc. So spend time on the vocabulary. Spend time reading the book. Talk like an engineer. Talk like a physicist. And things will go a lot smoother. Can you do the next one for me, please? Do the next one. Cool. Very good. Any more? Let's stop it. Everybody's saying B. Very good. Let's have a look at this. So we have, and again, I have to come down here. I have to say, well, what do I know? I'm going to say, well, my angular velocity omega is equal to 4 radians per second. I want to find my time, and I want to find how long it takes to go through a theta of 120 radians. And then I use my dimensional analysis, and I go, well, let's have a look. My omega must equal the distance I travel over the time, or the angle I travel through over the time taken. And then I do my math, and I rearrange, and I say, well, my time is equal to the angle I travel through over the velocity that I traveled with. And then I do my substitution, and I go 120 over 4, and then I go and I say that's going to be 30 seconds. Do you notice? The math was like the trivial bit. The math is this little bit at the end. I'm using, and I didn't learn this equation. I never sat down and learned this equation, but I know that velocity equals distance or displacement or something divided by time. So I'm using my general knowledge of a concept there. I'm making a list. Until I make that list, don't know how to do that problem. I'm not having you on there. I don't know how to do that problem. But when I make my list, I know how to do that problem. And it's that sense of what do I need to know, what do I know? My brain has the relationships in here. But that list prompts my brain to dig out that relationship. And then the rest is math rearrangement. The physics is here. The physics is on this side of the page. The math is on that side of the page. We need both. But if you focus on this side, then you'll find this side harder than it need be. Okay, so let's do some derivation. So this is actually going to be a lot easier than you might think. So here's a point in time. Let's just take this point in time. Lost my pen. There's my point in time. Here's my thing. I want to find my displacement, which is this value of x. X is equal to, well, it's a right triangle, isn't it? It's a right triangle. So it's just going to be, well, adjacent over hypotenuse is a cosine. So adjacent equals the hypotenuse times the cosine of the angle. the adjacent equals the hypotenuse times the cosine of the angle. So that was actually just trig. Well, okay, what about the next bit? Well, the next bit, I know that my tangential velocity is perpendicular to the radius. So I know if that is an angle of omega t, I know this is an angle of omega t. And I know if that's an angle of omega t, that's an angle of omega t. So I'm using a bit of geometry there to propagate my angles around. And then I say, well, I want the horizontal component of this tangential velocity, which is this horizontal red line here, which is the same length as that guy there, by the way. Well, now I have an opposite to my angle, and I have a hypotenuse. So my velocity, this opposite, my velocity is equal to the hypotenuse times the sine of omega t. Again, that's trig. I have the negative sign in because that's pointing to the left. If this is pointing to the right, and I called it positive, this has to be negative because it's pointing to the left on my diagram. Okay. And then down here, I say, well, my acceleration is the horizontal component of the centripetal acceleration. If that's omega t, then that's omega t. I want an adjacent. I have a hypotenuse. I say my acceleration is equal to, it's a negative arrow, so minus AC is the hypotenuse, cosine omega t is the trig function. And then I remember, oh, hold on. AC was equal to v squared over r, which equaled omega squared r. Well, r, of course, is my amplitude. I pull it round here and let it go, so it's my amplitude. So that's omega squared a. So substitute n. So I get AC is equal to omega squared a. So a is equal to minus a omega squared cos omega t. I substitute in for a. Let me have a look. I substitute in for AC. I'm sorry. I substitute in for AC, and I get this. And then, if I like, I can recognize. Oh, look! Didn't we see a cos omega t before? Oh, yeah, we did, and that was equal to x. So this equals minus omega squared x. It's trig. Mathematically, it's not hard. It's knowing what diagram to apply that to. That's really what counts. You could do the same thing using calculus. X is equal to a cos omega t. V is equal to dx by dt. That equals minus a omega sine omega t. A is equal to dv by dt, which equals minus a omega squared cosine omega t. So for some people, that's just so obvious. Why bother with the diagrams? And for other people, the diagrams are so obvious. Why bother with the calculus? When I worked in business, we had this a novel way of doing signal processing, and part of my job was to explain it to customers. And I remember with this one guy who was clearly bright. He worked for one of the national labs. He was clearly a sharp guy. Explaining it to him, and it was like trying to teach somebody to tie their shoelaces. He just was not getting it. And to me, it was so obvious. And then he said, just show me the math. And I said, oh, and on the back side I'd written the math. And he looked at it, and he goes, got it. And you could have shown me that math for a fair time, maybe even days, and I would have not been comfortable with it. But I could look at the diagram and I got it. And he needed the math, not the diagram. Some of us are very visual, some of us are very abstract. And the lucky ones are kind of in between. If you were on my baseball team and you could hit the ball like crazy, but you couldn't catch, what would I have you practice during the week?
You mean this
Pardon? I didn't catch it, sorry.
You can be the designated hero.
No, I'm going to be a coach. Which would I... Oh, I have no idea about designated hero. I only know there's catching and...
There's one that doesn't have to catch, just hit.
Oh, okay, not that. You're gonna learn to catch, aren't you? You're gonna do the bit you're not good at. The tendency we have is to focus on the bit we're good at and try and make it stronger. And what I want to encourage you is to spend some time focusing on what you're not good at to try and make it stronger. Yeah. Comment or question?
What it says there, like dv of the dt is equal to a minus a.
Wait, where are we on the page? Sorry. Oh, this guy here?
Yes.
Acceleration equals dv by dt?
Yeah, but what it says, like minus a w squared cosine y.
It's the same expression. Oh, sine it should be. I'm sorry. That is that guy there. It's the same expression.
No, I just don't understand what it says there. It's negative a w squared cosine y. It says there.
Omega t. It's the same expression.
Oh.
It's the same expression. Okay? Same expression, yeah.
V to T is tangential velocity, right?
Tangential velocity, yes.
What about V?
V is the x component of the tangential
Okay.
velocity.
Okay. And another question. What the y component of A, what does it stand for? What are the thing that we haven't talked about?
AC,
No, if you look at A,
that guy.
we have, no, you look at the circle on top of that one.
The circle on top. This guy, yeah.
We have A,
Amplitude.
we have X. What is the other one?
I don't know what the other one is.
The blue line.
The blue line. It's just a vertical line.
This doesn't stand for anything?
No, it's just because what I'm saying is the x component of the circular motion is the correct value for the simple harmonic motion. So that's just saying, oh, project this vertically downwards so you know how long x is. If you remember when we saw that video, we saw the circle was going round and round and round, and we compared the vertical positions between where the bob was and where the circle was. So we always compared the vertical positions. And that's what that blue line's doing, is comparing the vertical positions. Yeah. So the premise is the horizontal component of the circular motion is the same numerical values as the simple harmonic motion values. So the horizontal x for the circular is the x for the simple harmonic. The horizontal component of v for the circular is the v for the simple harmonic, and the horizontal acceleration for the circular is the acceleration for the harmonic. That's the principle. And it's done by observation. It's saying, oh, look, they're the same. A spring and block system, so you need to know those equations. Either you need to know how to derive them from calculus, or you need to be able to remember them or something. But those three equations are fair game. A spring and block system oscillates with simple harmonic motion. The block is moved 5 meters from its equilibrium position. As the block is moved 5 meters from its equilibrium position, the block is released, and the system has an omega, so omega angular frequency of 2 radians per second. What is the velocity of the block? V is equal to, that's my velocity. V is equal to, T is equal to 1.7 seconds. Now, before we jump into this, let's just think for a minute. So this is time going downwards. So this is time equals 0. And then time gets bigger as I go downwards. So 1.7 is somewhere on here. Maybe that's 1.7. Maybe that's 1.7. Maybe that's 1.7. Depends on the scale and everything like that. This language, angular frequency of 2 radians per second, I'm used to having frequency in cycles per second or hertz. So this angular frequency is a little bit disconcerting. And what you've got to recognize is that an oscillation is like this. There's 1 oscillations, there's 2 oscillations. And what I'm saying is I can represent that as circular motion. So that 1 oscillation is like going around this circle once. That would be 1 period. 1 period is like going 2 pi radians. If I went half a period, that's halfway through my wavelength, it'd be like going 1 pi radians. All right, my frequency in hertz is 1 over the period. My frequency in angular frequency is 1 over, or 2 pi over the number of radians. 2 pi because it's the number of radians in the circle. So don't be put off by this as 2 radians per second means that you've basically gone about that far around the circle. You're kind of like there. There's 1 pi, there's 2 pi. In 1 second. If you have 1.7 seconds, then you can figure out how far you've gone. So again, don't over-focus on the equation and be uncomfortable with what the parameters are. Play with the parameters and get to the stage where you're more comfortable with them. Let me get rid of this because we don't need it. So basically what we say is, I need a relationship. I need a relationship between these things. And so I say, well, I have an omega, I have a v, I have a t. And hopefully you get to the stage where you say, oh, I know this. X is equal to a cosine omega t. So v, which equals dx by dt, is equal to minus a omega sine omega t. Am I right? Is that the right expression? And then I get my calculator, my trusty calculator, and I do my calculation. So in order so that old guy who's grading you can actually spot when you're most of the way there and not, chide you needlessly for a little slip. It moved 5 meters. So we're going to put down A is equal to 5 meters. And I'm going to put down 5 in there. And my omega was the 2. And my sine is my sine. And my omega is the 2. And my time is the 1.7. Do as little as possible in your head. And that's going to be 3.4. So now I get my calculator. And can you work out the answer, please? I'm going to turn on the machine. Oh, I'm going to stop that. I'm going to turn on the machine and give me an answer when you've got it, please. Did I not turn it on? Sorry. So how are we doing? Let's just stop that. Cool. So let's see what people say. I got 18. Give me a few more of these answers. Come on. Come on. Give me a few more. Come on. Okay. So let's have a look. Let's stop it here. So stop. And let's see. Oh, some B, some C. I'd like you to look at your calculator and see which mode you are in. Okay. Got to be in radians. So the correct answer is 2.55. Okay. If you were minus 0.59, I suspect you're in degrees. Yeah. So watch out. Always, when we do in physics 2, we're always going between degrees and radians and degrees. And the trick is, if you're dealing with something that's got omega in it, you're going to be dealing with radians rather than degrees. So watch out for that. So that equals minus 2.55, so V is equal to plus 2.55 meters per second. You put it in a box. That is what I'd like to see if you get this type of question on a test. I can see that you visualized, I see your list of things that you are interested in, I see that you have your base equation, or if you don't want that base equation, you give me that base equation, but I see there's a principal equation that you're using. I like the fact that you put the numbers in so I can see, did you simply put the wrong number in the wrong space? That's not the same as not knowing the equation. It's still not good, but it's nowhere near as bad. And then, did you simply say 5 times 2 is 20 because you had one of those days, you know? And then I know you took care of the signs, and then you put units down. I give you 3 misses on units. If you miss units 1 time, I note it. 2 times, I note it. 3 times, last warning. 4 times, you start losing points. Quarter of the points from then on. Every time you don't put down units. Because mathematicians don't use units. Engineers and physicists use units all the time. Yes?
Are all of our tests like short answer questions?
They're all going to be open-ended questions, no multiple choice. Yeah. Cool. Yes?
X stands for displacement.
So X stands for displacement from equilibrium.
Okay, A, what does it stand for?
Amplitude. So at this time, A is equal to X. Here, A is not equal to X. Yeah? So, but A is a constant, etc. So notice from the language, I said you moved it to the right and let it go. I didn't tell you what amplitude was. I just told you what the amplitude was, provided you can visualize. And that's where the visualization comes in. This is not, do you know an equation, can you substitute obvious numbers into it? It's, can you interpret from the words what the visualization is? I am going to pause here, so I'm going to stop. I'm going to